So today we'll continue our subject about graphs, in this case we talked about finding clusters in graphs, which allows us to find groups of similar items. Let's look at what kind of data can be represented as a graph, and what kind of groups of people or groups of objects we would like to group together, and what they would represent if we group them together. So one example is a network. So there is lots of data that can be represented in the form of a network. One example is, for example, biological data. This is protein interaction data. So this data is showing interactions of proteins. So two proteins are connected if they interact or work together in a cell. So if there is a connection between two proteins, so the red dots are proteins, this means these proteins work together in a biological cell and they perform some function. And if we find groups of them, then the idea is to find clusters in the network to identify these functional modules that they create. So they create functional modules if they interact together in a cell. So if we find clusters on this picture, we're going to find proteins that work together in a cell. And if you look here, you will notice these are the clusters that we find. You will notice that these are not the well-separated clusters that K-means clustering would produce. That divisive clustering approaches will produce, but these clusters are overlapping. So what we see here is that these functional modules overlap with each other, or in other words, there are proteins that participate in activities in more than one functional module. Another type of data that can be represented as a graph could be, for example, a network of computers, right? So if you think about computer networks, if you think about the internet, what happens is that each of the dots or nodes here could be a computer or a machine or a device, your cell phone or laptop that is connected to the internet. And the links between them will show the distance that these machines are apart from each other. In that case, we can find groups of networked machines, or we can find groups of machines that are parts of the same network. Now, and so another type of data that can be represented as a graph, if you think about it, is, for example, so groups of networked machines, or it could be groups of pages that are linked to each other. Let's say pages, web pages that have hyperlinks to other web pages. This is an example that we did before for page ranking and computing the page rank of a page on a search engine. And so these could be pages and the hyperlinks between them. Can you think of another type of data that can be represented as a graph? You guys give other examples. There is one example shown on the board here, right? What is that showing? So we said network of computers, network of proteins, network of web pages. Anything else that can be represented as a graph? Yes?
Road network.
Road network, the network that connects the cities together. Okay, so that's a very good example. Which cities connects to which cities? There was roads. Very good. And we have another example here, which is showing what? Which people are friends with which people on the social network data, right? That's the Facebook data. For example, this data here is this data here this is a social network data. So this data is showing all the friends of a particular student. So each of these dots are the friends in the Facebook data that are friends with this person, and the edges that link them are showing that there's a friendship connection between them. So you're going to notice. So the idea here is, can we find clusters in this kind of data? So these are all the friends. They are friends if they connect to each other, and the goal is, what is the structure of this network, and can we find communities in here? If we were to do clustering, you're probably going to see that there is probably one big cluster where we see that dense region here. So you're going to see there is one big cluster here, maybe another cluster here, maybe another cluster here. So if we do clustering, we will think these are maybe some social communities that the friends belong to. Now, if we go and we ask that person what are actually his friends and what groups do they belong to, you're going to see something different from that. So that's going to look like this. So that person went and looked at his friends on Facebook, and he's saying that there is a group of students, a group of his friends that he went to the same high school. There's another group of friends that he did internships during the summer, where he made those friends while doing internships at various companies over the summer. And then there is two groups that he plays sports with them. The plays squash and basketball. And so what you will notice here is that these groups heavily overlap. So see there is an area here that you see. This is where these friends play both squash and basketball together with that person, and then over here these are the friends that both went to the same high school and spent time on the same internships, and so these and also play the squash and the basketball. So the idea here is that the clusters are not the type of clusters that you will discover with K-means, because K-means discovers that there are non-overlapping clusters, but they can be nested into each other and can overlap. So what the K-means will discover and what we have seen before is shown on the left picture. So this is the K-means will find clusters in round shapes that maximize the inter-cluster distances, so they have lots of edges in between the items, inside of the same cluster, and very few edges to nodes that belong to other clusters. And the idea is now that the clusters can overlap, so similar to what we have seen in the hierarchical clustering, because these red nodes here belong to both of the yellow and the green cluster. So we have nodes that belong to multiple groups at once. And because what we're looking for is for communities in this social network data. If we think about it, of how to represent that, there's something called the adjacency matrix. And so the adjacency matrix is very similar to that matrix that we have seen when we did the page ranking. Remember, you had this matrix that was showing a value of 1 if one of the pages has a link to the other page, and it was showing value of 0 if there is no link between those two pages. So this is called adjacency matrix. That's going to show the edges in the graph, that which node is connected to which node, or there is an edge between those nodes. So all the nodes will be shown on the left and on the top, and showing it each with each. So, for example, you see that the nodes in this dark orange color, these are the ones on the left cluster. They heavily link in between each other. So this darker shaded area here is showing that there is a lot of links between the objects here in this cluster. And then these objects don't have that many links to the bright green cluster, because there is only a few links here. For example, now, so that's called the adjacency matrix. So the adjacency matrix is going to be very similar to that matrix that we have seen with the page run. So what you see here, that was the matrix, adjacency matrix for non-overlapping clusters. But when we have now the overlapping clusters, so the idea is the people that belong to multiple groups are more likely to be friends with each other. In other words, the red nodes are more strongly connected with each other because they belong both to this orange group and to the green group. And so the adjacency matrix is going to show it will show a 0 or an empty space if there is no edge between those two nodes, and it will show 1 or shaded area if there is an edge. In other words, they are not friends if we're talking about social networks, and yes, they are friends if we have a 1 or shaded area. So let's say we have node I and node J, so the corresponding entry for those two nodes. If it says 1 here, this means that those two nodes are connected. This is the adjacency matrix. And so the previous adjacency matrix, you had seen two dark squares, one on the top left and one on the bottom right. And now you see that this darkest area in the right in the middle, that corresponds to the overlapping nodes. That it will be those red nodes. The area on the top left is the cluster on the left, and then the cluster on the right. So these would be the orange ones, these ones. another way to represent the graph. So we can think of the network as a big matrix. And the empty spot means that given pair of nodes is not connected, and the dot means that the pair of nodes is connected. So the densely connected nodes have a darker shaded area. So if we are to look for communities, then we can think of these communities as tiles. So each community is represented as a tile, and the thicker the tiles are, the more groups a particular person belongs to. And so the idea is that we want to, so the more groups overlap in a certain region, the thicker the tiles are. In other words, there are more nodes, there are more edges between the nodes in the network. And what we want to do using this view is that we want to take out these tiles one by one and decompose the network, because we're looking for communities. So each one of these tiles will represent one community. So we want to take the tiles out one by one from the network.